Howdy, this is a video on the associative axiom. We're building a simple mathematical system, axioms for addition. This is based on the Suppess textbook. In section 7.1, we developed the commutative axiom. That is, for all x and for all y, x plus y is identical with y plus x. We also developed some definitions. We defined the number 2, 3, 4, and 5. And this basically served as a set of premises which we then derived various theorems from. Now, addition might be called a binary operation in that we are only adding two numbers. But we can have an addition problem like this, x plus y plus z. To keep it as a binary operation, let's add parentheses. There are two ways to add parentheses here. We can group the x plus y, or we can group the y plus z. So if we have something like 3 plus 2 plus 1, we can group the 3 plus 2, or we can group the 2 plus 1. But because this and this result in the same sum, let's develop the associative axiom. That is, there are two ways of associating x plus y plus z such that it leads to the same result. And hence we have the associative axiom. We have three variables. We have three quantified variables. For all x, for all y, for all z, parentheses x plus y, close parentheses, plus z is identical with x plus parentheses y plus z, close parentheses. So this statement here and this statement here are identical. But note, this is not true of subtraction. So subtraction is a non-associative binary operation. Driving some theorems. We're given a toolbox, and within this toolbox we have the commutative axiom, the associative axiom, some definitions, and just like in the last video, just like in the last section of the Suppess textbook, these are our starting premises, and we can then derive various theorems from those premises. Moreover, when we prove a theorem, it then becomes a part of our toolbox. We can then use that theorem as a premise in further proofs. For example, Theorem 10 states that 4 is equal to 2 plus 2. We want to prove that, but we can only prove that with our toolbox. We cannot resort to any other premises. So what do we have? We have the definition of 4. 4 is identical to 3 plus 1. We also have the definition of 3, which tells us that 3 is identical to 2 plus 1. So what I'm going to do for the first line to make things clear, I'm just going to state the definition of 4, that 4 is equal to 3 plus 1. And that's just a definition of 4. That comes directly from our toolbox. However, we know by the definition of 3 that 3 is equal to 2 plus 1. So essentially we could substitute that 2 plus 1 into that 3 by our identity rule. Hence for line 2, we'll say that 4 is equal to parentheses 2 plus 1, close parentheses, plus 1, by the use of the identity rule with line 1, which is the definition of 4, and with the definition of 3. So oftentimes we're going to be substituting and we're going to be rearranging. We're going to be rearranging with the commutative axiom and rearranging, so to speak, with the associative axiom. And here's exactly when I believe we should use the associative axiom. We should instantiate that. So then the question is, what do we instantiate for x? What do we instantiate for y? What do we instantiate for z? And I think we should instantiate 2 for x, 1 for y, and 1 for z. So for line 3, we can get parentheses 2 plus 1, close parentheses, plus 1 is equal to 2 plus parentheses 1 plus 1. So that's the universal instantiation of our associate axiom, where x is equal to 2, y is equal to 1, and z is equal to 1. Because if you notice line 2, we're told that 4 is identical to parentheses 2 plus 1, close parentheses, plus 1, And so we can substitute that 4 into this left-hand side, so to speak, in terms of line 3. Hence, for line 4, we can say that 4 is equal to 2 plus parentheses 1 plus 1, close parentheses, by the use of the identity rule with lines 2 and 3. And then finally, we know the definition of 2, according to our toolbox. 2 is identical with 1 plus 1, so we can substitute a 2 for that 1 plus 1. Hence, for line 5, we can say, therefore, 4 is equal to 2 plus 2 by the identity rule with lines 4 and the definition of 2. What about theorem 12? We want to prove that 3 is equal to parentheses 1 plus 1, close parentheses, plus 1. We can do this in just one line because, after all, we know the definition of 3. 3 is equal to 2 plus 1, and we know the definition of 2, that 2 is equal to 1 plus 1. So for line 1, we'll say, therefore, 3 is equal to parentheses 1 plus 1, close parentheses, plus 1, by the identity rule with the definition of 2 and the definition of 3. Because notice the definition of 3 is 2 plus 1, but this 2 is identical with this 1 plus 1, so we just substitute that 1 plus 1 in for that 2 plus 2. So that's how we got that. And then we have theorem 16, 2 plus 5 is equal to 3 plus 4. Okay, for theorem 16, I'm actually going to erase the other answers because I'm going to have, I didn't make sure I have enough space, so let me just erase all this here. Okay, so for theorem 16, what should we do? We have 2 plus 5 is equal to 3 plus 4. Well, I think a mini goal of this proof is to prove 5 is equal to 3 plus 2. I think that's going to be a main thing we're going to have to do. But for now, for line 1, we can say that 2 plus 5 is identical to 2 plus 5. And that's just a logical truth. And then we can worry about the right-hand side. Because we have a left-hand side down, we got 2 plus 5. Although that doesn't mean we're not going to have to play around with the left-hand side as we go through the proof. But in a situation like this, when you have, two different numbers, say, on the left-hand side, we're probably going to have to resort to the logical truth rule to at least get us started. Anyways, our goal right now is to say that 5 is equal to 3 plus 2. And we don't have that in our toolbox. And so, for line 2, just to remind us, we'll just say that 5 is equal to 4 plus 1, and that does come from the toolbox. That's just the definition of 5. And then we can use the identity rule because we know the definition of 4. 4 is equal to 3 plus 1, so we can substitute that in for that 4. So for line 3, we'll say that 5 is equal to parentheses 3 plus 1, close parentheses, plus 1. So this is the identity rule with the definition of 4 and with line 2. And then for line 4, let's say that, let's use the associative axiom. Okay, so we'll say x is equal to 3, y is equal to 1, and z is equal to 1. So we'll say that 3 plus 1, in parentheses, then plus 1 is equal to 3 plus, in parentheses, 1 plus 1. So this is the universal instantiation of our association or associative axiom, where x equals 3, y equals 1, z equals 1. because by doing that, we can say this 1 plus 1 here is identical to 2 by the identity rule. So for line 5, we can get parentheses 3 plus 1, close parentheses, plus 1 is equal to 3 plus 2 by the identity rule with line 4 and with the definition of 2. And then we can do another identity rule with this 3 plus 1 here. That's just 4. So for line 6, we'll say that 4 plus 1 is equal to 3 plus 2 by the identity rule, line 5, and definition 4. And then, because we have this 4 plus 1, we know that's 5 by our definition of 5. So for 7, we can get 5 is equal to 3 plus 2 by the identity rule, line 6, definition 5. And this is important because this is going to allow us to do something. Because we have here that 5 is identical to 3 plus 2, and then notice line 1, we can get that 3 plus 2 for that 5. So for line 8, we will say that 2 plus 5 is equal to 2 plus parentheses 3 plus 2 by the identity with line 7 and 1. For line 9, let's resort to the commutative axiom, because we're going to want to say that 2 plus the quantity 3 plus 2 is the same thing as the quantity 3 plus 2 plus 2, because then we can relate lines 7 and 9 through the identity rule. So let's just say that 2 plus parentheses 3 plus 2 is equal to, in parentheses, 3 plus 2 plus 2. So that's the universal instantiation of our commutative axiom, and x is equal to 2, y is equal to 3. So that just showed, of course, we just reversed this quantity and this quantity. And then for line 10, as I said, we can say that 2 plus 5 is equal to parentheses 3 plus 2, close parentheses, plus 2 by the identity rule with lines 7 and 9. And that's how we interrelated them. That's why we need the commutative axiom. But now we're going to need the associative axiom. If we say that x is 3, y is 2, and z is 2, we'll get for line 11, parentheses 3 plus 2, close parentheses, plus 2 is equal to 3 plus parentheses 2 plus 2 by the universal instantiation, associative axiom, where x equals 3, y equals 2, and z equals 2. And now we can use this fact to get to the identity rule. We're relating lines 10 and 11. So for 12, we can get 2 plus 5 is equal to 3 plus parentheses 2 plus 2, close parentheses, because the identity rule with lines 10 and 11. And then look, we do know that 2 plus 2 is 4 by theorem 10. So theorem 10 is in our toolbox. Thus, for line 13, it therefore follows that 2 plus 5 is equal to 3 plus 4 by the identity with lines 12 and theorem 10. And we approved theorem 16. Please allow me to make one correction. Y is not equal to 3 on line 9. Rather, y is equal to 3 plus 2. And x remains the same. X is equal to 2. Because the quantities that were flipped with the commutative axiom were 3 and 3 plus 2. Briefly, let's look at exercise 5a, and we'll do 3 problems. It's kind of interesting because we're to give proofs for the following theorems of logic. For example, theorem 1 is that for all x, if x is an f, then a is an f. Intuitively, that's correct. It has to be a true statement, but how could we actually prove that? It is a conditional, therefore this suggests a conditional proof. Hence, for line 1, we'll just assume for all x is an f by assumption. And then we can instantiate that for line 2. We'll substitute a for x, so this is the universal instantiation of line 1. And we've already reached that consequent fa, so outside of quarantine for line 3, therefore it follows for all x, if x is an f, then a is an f, by our conditional proof with lines 1 to 2. What about theorem 2? We have if p, then q or p. This textbook doesn't require parentheses. Some would require it to be placed around this disjunction here. But in any case, this is also a conditional, so we should do a conditional proof. And intuitively, that makes sense as an argument. So if p is the case, then p will be the case. And we can always place something in a disjunction relationship with another as long as at least one of those options is true. For line 1, we'll just assume p and place it under quarantine because it is an assumption. And then for line 2, we can say q or p by our law of addition with line 1. And already we got that consequent. So for line 3, therefore if p, then q or p by our conditional proof, lines 1 to 2. What about theorem 5? It's another conditional, and just to help matters, I'll put some parentheses for the antecedent and for the consequent. So we have if 3 is equal to 2 plus 1 and b is equal to 3, then 2 plus 1 is equal to b. So let's just assume that antecedent, 3 is equal to 2 plus 1 and b is equal to 3. And then we can simplify. For line 2, we can get 3 is equal to 2 plus 1. This is the simplification of line 1. And then we can also get b is equal to 3 by the simplification of line 1. Some textbooks would require you to do the commutative rule in line 1 before you get b equals 3 by simplification, but the Suppess Hill textbook doesn't require that, thankfully. And now we can do some identity rules. This is just an algebraic problem, right? We're saying that 2 plus 1 is equal to b. So for line 4, we can say b is equal to 2 plus 1. By the identity rule, lines 2 and 3, we just substituted that 2 plus 1 in for that 3. And then for 5, we want 2 plus 1 on the left-hand side. Right now it's on the right-hand side. So let's just say that 2 plus 1 is equal to 2 plus 1. That's a logical truth. And then we can do the identity rule again. We can get 2 plus 1 is equal to b by the identity of lines 5 and 4. And now we have that desired consequence. So outside of quarantine for line 7, we can say if 3 is equal to 2 plus 1 and b is equal to 3, then 2 plus 1 is equal to b by our conditional proof with lines 1 through 6. Let's return to deriving some theorems like we did a couple slides ago. I think last time we did theorem 16, if I'm not mistaken, we have the same toolbox. It has the commutative axiom, the associative axiom, etc. This time we want to prove a conditional for all x. If x plus 3 is greater than x, then such and such follows. It is a conditional, so this implies that we should do a conditional proof, and we'll just assume that antecedent. Hence for line 1, we'll just say for all x, x plus 3 is greater than x, and this is just an assumption. And because it's an assumption, we have to place it in quarantine. And then the question is, what do we instantiate for x? Well, note that we have this 2 plus 5 here, and that's right after this greater than sign. So I think the way to go forward is to actually instantiate that for x. Hence we have parentheses 2 plus 5 plus 3 is greater than 2 plus 5 by the universal instantiation of line 1. And we're going to have to work with that 2 plus 5 plus 3. And one way is to take use of the associative axiom, because we're going to have the left hand and the right hand side just displaying different groupings of that. So for line 3, we'll just say parentheses 2 plus 5, close parentheses, plus 3 is equal to 2 plus parentheses 5 plus 3, close parentheses. So this is a universal instantiation of our associative axiom, where x is equal to 2, y is equal to 5, and z is equal to 3. So now note that we can use this fact that this right-hand side is identical to this left-hand side. So we can replace this with this, because we're just going to be using the identity rule. Hence for line 4, we'll say that 2 plus parentheses 5 plus 3 is greater than 2 plus 5. This is the identity rule with lines 2 and 3. For 5, we're going to use the commutative rule, because what I'm going to do is, instead of having this 5 plus 3, I think it will be better as we go through the proof to have it at 3 plus 5. So we have line 5. 5 plus 3 is identical to 3 plus 5. Universal instantiation of our commutative axiom that x equals 5, y equals 3. And then we can resort to the identity rule to get the 2 plus parentheses 3 plus 5, close parentheses, is greater than 2 plus 5, with the identity rule with lines 4 and 5. But as we move on, I'm going to regroup these things. So instead of the 3 plus 5 as being grouped, how about the 2 plus 3? So for 7, we have 2 plus 3 in parentheses plus 5 is equal to 2 plus, in parentheses, the quantity 3 plus 5. So this is the universal instantiation of our associative axiom. X equals 2, y equals 3, z equals 5. So now, because of that regrouping via the associative axiom, for line 8, we can now say parentheses 2 plus 3, close parentheses, plus 5 is greater than 2 plus 5 by the identity rule with lines 6 and 7. there's a lot of things that have to be reshuffled, so to speak, because we ultimately want 1 plus 2 plus 3 plus 4. And now, because of that, let's get in a 4 plus 1. We can use the identity rule to get that 4 plus 1 in for that 5. So I think that's a good move. So for line 9, we can say parentheses 2 plus 3, close parentheses, plus parentheses 4 plus 1, close parentheses, is greater than 2 plus 5 by the identity rule with line 8 and with the definition of 5. Oof. Let's see if I can. For line 10, we'll use the associative axiom once again. And this time, let's see, we'll say parentheses, 2 plus 3, close parentheses, plus 4, close parentheses, plus 1 is equal to parentheses 2 plus 3 plus 4 plus 1. So this is the associative axiom, or the universal instantiation of it. So we have 2 plus 3 is equal to x. We have 4 is equal to y. And z is equal to 1. Because now we can use the identity rule once again, because we have this here, we can get that for this. Hence for line 11, and I'm sorry about this big mess of stuff, there's a lot of steps here. So we have, let's see, parentheses, 2 plus 3, close parentheses, plus 4, close parentheses, plus 1 is greater than 2 plus 5, because we have the identity rule with lines 9 and 10. Now we are getting closer. We have this plus 1, but we want the plus 1 in the front, so we're going to have to resort to the commutative axiom. And so for line 12, we'll say parentheses, 2 plus 3, close parentheses, plus 4, close parentheses, plus 1 is equal to 1 plus parentheses, 2 plus 3, close parentheses, plus 4, close parentheses. So this is the commutative axiom, the universal instantiation of it. And x is equal to parentheses 2 plus 3, close parentheses, plus 4, and y is equal to 1. So now we can do the identity rule. So for line 13, we have 1 plus parentheses, 2 plus 3, parentheses, plus 4, parentheses. I can write that a little better if I can. No, not much better, but a little bit better at least. Okay, it's greater than 2 plus 5. So that's just the identity rule with lines 11 and 12. Okay, so what should we do for our next line? Well, it appears that we're going to have to rearrange the groupings. We're very close, so we're going to have to do the associative axiom. Because we want, when we look at this, we have this this whole quantity, 1 plus parentheses 2 plus 3, close parentheses, that whole thing within parentheses, so to say. So let's try that. We'll say that, let's see, parentheses 1 plus parentheses 2 plus 3, close parentheses, plus 4, is equal to 1 plus parentheses, 2 plus 3, close parentheses, plus 4, close parentheses. So this is just the universal instantiation of the associative axiom. And x is equal to 1, y is equal to 2 plus 3, and z is equal to 4. We're still in quarantine because we're doing this based on an assumption. But now we can do our identity rule, and then we can get parentheses 1 plus parentheses 2 plus 3 parentheses plus 4 is greater than 2 plus 5, and this is the identity 13, 14. And now, because we've reached that consequent outside the quarantine for line 16, we can say therefore it does follow for all x, if x plus 3 is greater than x, then parentheses 1 plus parentheses 2 plus 3 parentheses plus 4 is greater than 2 plus 5. And that's based on a conditional proof with lines 1 through 15. And that is our final answer. We will continue to work on the textbook First Course in Mathematical Logic by Patrick Suppess and Shirley Hill as we build a simple mathematical system. Now this simple mathematical system, by the way, is essentially a group. Now a group is an idea that comes from abstract algebra. It's kind of interesting, and in the next video I want to cover this a little bit more, but a group, let's just call it G, essentially is just a set of elements together with a binary operation. This binary operation might be addition, it might be multiplication. In our case, obviously, it's addition. And there are certain properties that a group must have, in order for it to be a group. For example, you need closure. That is, if you have A star B is equal to C, with that star just being our binary operation, such as addition, and A, B, and C all belong to G, you then have the principle of closure. So C better belong in that group. Now, by the way, in the Suppess and Hill textbook, in terms of our toolbox, we have defined the numbers 1, 2, 3, 4, and 5, and that's it. So if we said 5 plus 1 is equal to 6, we've already violated the closure principle because 6 does not belong to our little set there. However, we can say 5 plus 1 is equal to 1 plus 5 and all sorts of other things. However, the Suppess and Hill textbook could have modified our toolbox a little bit and said, instead of just saying we have the numbers 1, 2, 3, 4, and 5, we have infinitely many numbers. We have the set of all integers. That's certainly possible. Okay, and integers, that's going to obey the closure principle. You add an integer with another integer, you're going to get an integer, right? So a group has a closure principle or property or axiom, if you will. It's also going to uphold associativity, and that's what we covered in this video. And then the next video, we're going to be covering what's called identity here, when we build an axiom for 0, and also there should be an inverse. So these are the 4 properties that make a group. And by the way, it doesn't include the commutative rule, okay? Or commutative axiom. So the commutative axiom is not essential to a group. But if you have a group that's also commutative, you have an abelian group. So as we continue through this textbook, I want to at least a little bit connect what we're doing to abstract algebra. It's obviously, to be sure, somewhat minor, but there is a connection nevertheless, and I want to a little bit highlight that. I'm certainly no expert in abstract algebra. It's a very big, complicated subject, but I do know at least a little bit about it, so I'll talk a little bit about it as we continue through the textbook. Thanks for watching, and up next will be the axiom for 0.